SkillStruct presents.
Hey everyone, it's Michael here from SkillStruct, and today we are honored to have George Heineman from the Polytechnic of Worcester, who is an associate professor of computer science. Today, in this part of our series, we're going to be tackling the algorithm. George, thank you again for coming onto the platform. Welcome to SkillStruct Presents Tech Series.
Thank you. I'm so glad to be here.
Thank you, George. And I guess the first question, we normally ask this question, is a favorite of ours. What is your programming credentials? How did you get started in programming? We're going to tie it into algorithms as well. So yeah, please let us know how you started programming.
So like many people of my generation, we discovered computers when we were in our early teens. I first got a small Radio Shack, Tandy Radio Shack computer that had a cassette tape and 4K of memory. And that was my first computer. And it was the most amazing thing that you've ever seen because you could do things on it that you can't do in real life. And it was surprisingly satisfying to draw images and watch them move about on the screen. And that just was the hook that got me involved in developing things you couldn't do in the real world. And so those first early years of programming, you're just learning a new thing that had never been sort of discussed before. And so I learned how to program games. This is usually where most programmers start. And then I moved into some more technical things because my high school actually hired me to help write some software for them. And so there I was as a junior in high school, 16 and 17, getting paid as a programmer. So that was a very interesting beginning for me and how I started programming. And that was when I was, like I said, 16. So that was 1982 and 83. And then since then, I just haven't stopped.
Awesome. And in terms of algorithms then, because obviously, and we're going to talk about your book, obviously, Learning Algorithms. You've obviously dealt with that space for quite some time, I think about 20 years plus. How did you get into algorithms specifically? What made you, focus on that with your career?
So when you start programming, it's surprisingly, it's a surprise to me, that, at least, at how bad your programs can be. Because you're not really spending enough time understanding the right way to do things. You're just feeling around in the dark. And it's kind of like if you're doing a DIY, you do-it-yourself projects at home, you kind of build some things, but they don't really stack up when compared to the professionals. So when you really want to look at the programs you've written and try to make them better, because you know that there are better programs out there, you got to dive into the details and really try to figure out what the experts are doing that you're not doing. And so it starts with learning data structures, like binary trees, linked lists, things like that. But then it goes further to really trying to understand how they're able to write programs that are fast, that seem to solve the problems you're trying to solve, but they do it in 10 times faster than you do. And that's usually the basic idea. How can you improve the speed of your programs? And the way to do that is to learn the fundamental algorithms that have been developed over the last 50 plus years. And the best part about algorithms is they're ideas that are out in the community. And so once you find an algorithm, you can implement it yourself. There's no barrier. You don't have to pay a license. You don't have to secure a patent or something. At the early days of computer science, these were just good ideas and everyone just grabbed them and ran with them. And so you can learn how to program more effectively if you spend a little time looking at algorithms and how they've been used to solve problems.
Okay, that's interesting. And you touched on examples like binary trees and linked lists, and we're going to touch on examples a little bit later. And so essentially your answer is, to be as efficient as possible. And that's what you really chose, learning algorithms. So your programs could be really efficient to the point where they can obviously perform at the maximum capability. Is that fair to say?
Yes. Yep.
Okay, and so we're talking about algorithms today. Let's just set the scene of what is an algorithm. The reason why I say that is there's a lot of people who may be casual technologists or casual people who may have heard of this word, the algorithm, or it's the algorithm's fault. Perhaps it's sometimes used as a scapegoat. Just in layman's terms, why don't you explain to us what is an algorithm?
Okay, so I'm going to mark a moment in time when we actually had computers, because before we had computers, you had mathematicians and people who could work things out on paper. But once you have a computing device, then you can now truly have for the first time an algorithm, which is a step-by-step problem-solving method that you can write up as a computer program and have it run on a computer to produce the desired output you want in a fixed amount of time. Like it can't run for 10 years. It's got to come back in a reasonable amount of time. And so we've had recipes for thousands of years, but they require humans to understand how to put everything together, or even a step-by-step manual that you could read. You still need to have someone of intelligence to be able to take that and carry out those steps. But where an algorithm comes in, it's really interesting. You give it to a computer, which is very simple, but it's blazingly fast. And so if you tell it exactly what to do, it will do it much faster than anything that we could do. And so those algorithms are just solving problems. And the best part is, these are problems that most humans don't want to solve because they just take far too long. But if you have a computer program that can just run for endless speed, and they're so powerful nowadays, they can solve problems that humans just wouldn't have time to solve, then you can do some really interesting things.
Okay. Sounds really interesting. And what about people who may have a negative, feeling of algorithms? We sometimes hear it compared to the 7 deadly sins, lust, gluttony, envy, etc., etc. What's your thoughts on, potentially companies leveraging it by tapping into the 7 deadly sins? Is that a myth, or how would you sort of respond to that?
Yeah. So the thing that's really interesting about algorithms is that they're trying to solve problems. Something like, compute the value of pi. That's a very mathematical problem. But then there's more human-oriented problems, and you can apply algorithms to solve those same problems. Things like, should I give this person a loan? What news should appear in my feed when I go to Facebook? And so those are human problems. And if you're not careful, the algorithm itself could do something that's in a rather dehumanized way. So, for example, if a company decides who's giving out loans to people, if they decide to let an algorithm decide who gets the loan or who doesn't get the loan, well, you could have implicit bias in there, and some people could just not get a loan. And you could try to say, oh, it's just the algorithm and just running the math, but that's a very human problem. And so the algorithm has no concept of community or humanity. It's just trying to solve a problem of numbers. And so the real challenge is making sure that the problems that you're solving still retain that human element. So to get to your point you just asked, is that an algorithm can actually give you as a company a competitive advantage, something that you have, a proprietary secret sauce, I guess you would say. And so that could give you an advantage in the marketplace, which means that your company grows and you can get better revenue and lead to other further inventions. And so those are the things that algorithms can let you do. Where before, say in the Industrial Revolution, you would get a patent, and then that patent would give you the opportunity to amass a company that knows how to build trains or serves oil or is a bank. And those lead to incredible wealth growth. And so algorithms can do the same thing, because now we're in a digital revolution. And so they give you as a company the competitive advantage. Now, will that automatically lead to the 7 deadly sins? Not necessarily. Just because you are the dominant company, like say IBM was in the early days of computing, they were the #1 company, but they were just big. I don't necessarily believe that they were full of greed or were slothful because of that. But it's true that the algorithms themselves can give you that advantage, and then you can use it for, I guess, good or ill.
Got you. And so you're saying there's, it's basically, as I understand it from your explanation, algorithms are just algorithms essentially. And, when it comes to, the 7 deadly sins and stuff like that, it's not a thing where it can, in theory, invoke that. It's to do with more of human interaction with the algorithm as opposed to the algorithm itself. Is that a fair?
So if you look at the algorithm as being a tool, then tools by themselves are only as good as the human who wields them. And so that is just another kind of tool that could be used. And so if I think about the ability to use algorithms for good, there's all kinds of things that we can point to, like the internet is available because algorithms allow internet traffic to flow efficiently. And without, everyone should know that the internet is based on this network, and there are these devices called routers that send traffic all around the world from one computer to the next. Every router has these algorithms that knows how to do that efficiently. And without the routers, then we would have no internet. So to me, that's a good thing. Those algorithms have actually improved the distribution of information, transparency, education. At the same time, naturally, you can use those same tools to try to be either totalitarian or to try to take ownership of some area and dominate against your competitors. So there's the way that I would argue is that it's just a tool, and it's how you use them that leads to societal good or to ill.
Got you. And that segues nicely into, obviously recently we've had in the news social media companies like Facebook, now Meta, and other companies like Instagram, which actually is owned by Meta as well. But just let's keep it general. Let's say social media companies about leveraging the algorithm when it comes to likes and really playing on people's seven deadly sins, as it were. What about that then? People using, or companies using the tools for negative outcomes. Is that a thing then? Could you actually leverage algorithms to actually evoke certain information though?
Yes, and so this is a very important discussion. There's a long history of this. If you go back to when Google was founded, which was founded by Larry Page and Sergey Brin, they came up with an algorithm they called PageRank, which allowed you to very quickly find the right content. And they determined right content as in a trusted source. So on the internet, if you ever go to a web browser, you see a link and you click on it, it brings you to someone's web page or some other website. And so the more links that go to the same place would increase the trust that you might have that it's a reputable source. And so Google first made all of its money by being a search engine that let you find exactly what you were looking for, because it indexed the web and made it easy for you to find things you didn't even know existed. So that was really positive, right? And then you slowly moved into those different other social networks that came on. I'll actually mention one that is not a social network, but was dominant. So Netflix. Netflix came on as this really amazing company that wanted to deliver DVDs right to your door. And they had a prize, this is back in 2000, I think 2007, where they offered $1 million prize if someone could develop an algorithm that could increase their recommendation accuracy by 10%, right? This is where you watch a movie and then Netflix says, hey, based on the movie you watched, I bet you'd like the following movies. And naturally, if they recommend a movie with higher accuracy, they can raise more money because people find out about movies they didn't know they like, and they keep going back to Netflix for that experience. So that was one of the first social engaged networks, algorithms, that really improved their bottom line, because if you could give better recommendations, then you'd have people keep coming back to your site. And now the one that started your discussion is the whole Facebook Meta issue. And so when they came on the scene, they had this really great idea of connecting humans together. And so you can go to their place and see what your friends are doing, and you can post what you're doing. And even though it seems like it's just years of history, it's only been about 15 to 20 years ago, the first thing they had was a like button. If you see what someone posted, you could like it. And that gave some really good feedback from you to that person. And hopefully it was one of your friends, so that you knew who they were and you wanted to send them some love that day. But eventually, as the network grew, they needed something more to try to represent what you might like or not like. Because the idea there was, if you like some content, maybe they can use that to provide you with more content like it. Again, that same Netflix idea. Try to recommend things to you that you might like. And then they made a little shift. And again, no one really remembers because it seems like they've been there forever. But back around 2016, they added more reactions. It started out, they only had a like button. And they initially had plans to have a dislike button at the same time, but they decided when they started the company, they didn't want to be in the business of sending negative downvotes. They only wanted to have upvotes, which is a very nice thing. But then in around 2016, they added 5 more. And these are the ones where you've got love, you've got sadness, you have the angry face, you have the wow face, and then the laughter. Now, if you look at those things, the one that stands out to me is the angry face. So all the other ones were in line with sort of Facebook's idea of connecting humans together. Do you like this? Are you sad? I'm with you as well. Are you wow? Are you excited? Are you laughing? But then there's that angry face. And the reason why this became an issue is because, well, if you show that you're angry on something, what should Facebook do with that information? And there was a time when on Facebook, they had a little news feed on the right-hand side that would show you active news. And so they have a weighting scheme. That's their algorithm that says, based upon your reactions and based upon everyone else's reactions, they're trying to figure out what content to give you. And so they had this algorithm that would weight the information based on, did someone like it? Did they love it? Were they angry? And so what they turned out is that they added 5 times the effect of the anger as opposed to just the like. And so as more and more reactions appeared and more were either love or hate, then they became more, they had more of an impact on the ranking scheme. And so those things that people hated more would start to rise to the top. So here's a situation. So this is just the algorithm doing what it's told to do. I'm trying to provide feedback to you. And so the things that you liked, I'll give you more of that. But the things that you hate, I'll give you more of that as well. And so you see that it led to this opportunity where they were trying to drive people to their site and generate revenue, because that's what they do, just like Netflix is trying to generate revenue. But inadvertently, they're raising the things that get people angry. And that's the stuff that really became an issue. And we're starting to find out more about this because this is internal discussions of the company. And every now and then some of this stuff gets leaked out as to how they go about it. And there were some employees that were very sort of nervous about this idea that you're promoting something that someone hated as a way to drive someone to click on it. And so they eventually, just 2 years ago, they came up with that final 7th reaction, which is the care reaction. This was done in reaction to the pandemic and to try to give people a way of showing, it's not that I don't love you or don't like you, I'm trying to show care to build the community. So they did come back in a way to the original roots. And now they've since changed their ranking scheme so that if someone says that they hate something, they're really angry at it, that no longer has a role in promoting their content. That they now have a weighting scheme that if you love or you care something, that's a 2 times effect as opposed to just liking, which has a 1 effect. So there was this time for 5 years when they were really promoting content based upon whether someone hated it. And that's sort of what was the problem. Did it give them more revenue? Possibly, because as you know, there's also the larger societal issues that we have from just regular network broadcasting. The idea on the nightly news, at least in America, one of the ideas was, well, if it bleeds, then it leads. So the idea that the nightly news has to have that one item that's going to get you to watch because you're going to be so upset, you've got to watch it. Mm. And that transferred over into the social networks. So it's all about trying to have a balance. The algorithm is just there to do a job that are just automatic. But if they leave out the fact that it has an impact on the human or the impact on the community, that's where it starts to go sideways.
Wow, that's so interesting. I mean, there's so many things to pick up on in there, how you ultimately came down to how obviously traditional media do things in one way, and now it seems to be more and more replicated, with social media in particular, and that's quite fascinating. You also mentioned that shift in 2016, and one may be able to argue that social discourse really dramatically changed over the past sort of 5 or 6 years since those introductions, and maybe that can be the pinpoint. So in a sense, conscious decisions by tweaking the algorithm has led to potentially some social discourse. Obviously we're recognizing it with these leaks from, whistleblowers from Meta, for example, but, just seeing all of these things with algorithms, I guess one can understand why people, whenever they hear the algorithm, where they just associate it with, 7 deadly sins, for example, or other negative connotations, but perhaps it's the people behind the algorithms, really and truly. That's where the negativity should be more focused on than the algorithm itself.
Yes. Wow. It's a very changing dynamic as well, because Facebook, there was no company like it at all. And so when they make a small change in the algorithm, it may have a ripple effect, and then everyone adapts and adjusts to it. So there's a lot of experimentation that they were doing, and they didn't realize or think ahead in advance as to the impact that it would have. And only after they saw the impact did they realize, we have to change the way we do things. And that's where we hopefully will get to in the future.
Yeah, hopefully. I mean, I think even with YouTube, for example, I think they are banning the dislike, or they're doing something where they're not really promoting the dislike buying anymore, and they're more saying, they're only showing likes and making likes more visible than the dislikes. With, there's nuanced opinions on either side, but I think people or companies are recognizing that consequence of tweaking with algorithms that's really sensationalized discourse, like we were saying before. So, like you say, we hope that hopefully, that there is a more conscious effort towards that. And, we're talking about algorithms and things like, the consequences and things like that. There's, on the converse, obviously positive things. And I wonder, have you seen, algorithms be used in a positive way as well, just to balance out the discussion?
Sure. So what I'm going to first talk about is this new field called machine learning. And the reason why I mention that is because there's now been a shift in not just computer science, but in every discipline, because algorithms are ways to make these really good ideas a lot faster because you run them on a computer, and then you can produce all kind of very effective ideas. One of the things that machine learning did is it changed the very nature of what an algorithm is. So it's worth explaining that. So a regular algorithm, let's come up with one. So there's one called binary search. So if you have a list of names and they're all in sorted order, and you put them into a phone book, like when I lived in New York City, it was about 2 inches thick. And that was the list of all the people in New York. And so you wanted to find a person, you just look it up there. Now, we're humans, and so we know not to just start on page 1 and read until we get to the name. We know, just divide the book in half and then see which side the person's name is. And then every time you cut the book in half, you get closer and closer to the target. And so that's a concept called binary search, which is really efficient at locating something in a sorted list. And so that particular algorithm is played out all day, anywhere you are, because that's how computers store information, to make them very efficient. So we take that as an idea, and then that allows all kinds of websites to effectively search for things when you type in a keyword and you quickly find something. Now, that's a very simple algorithm. If you shift to this idea that we're in now, this era of machine learning, you have a bunch of input, let's say pictures, and you want to try to find all the pictures of buildings that might look like they're in need of repair. And so what you do is instead of writing an algorithm, which is rather complicated, by the way, to take an image and try to figure out how do you decide whether a building is in repair or not, or how you would fix it. You instead give it to this machine learning algorithm, which takes hundreds of thousands or millions of pictures, and it essentially computes the logic that you would use to determine, just by a picture itself, is that building in repair or not in need of repair. And so this is what the modern word for algorithm has shifted towards, and it's a machine learning algorithm. And so the reason why this is relevant is because when you train a machine learning algorithm, you start with an input set of all these original things, and they're typically pictures, but it's now been expanded to medical data. And if you're an athlete, you've got your biometrics that you have, and so you can have hundreds of thousands of seconds of your body signals to determine what your optimal performance is. And instead of writing an algorithm for that, you give it over to the machine learning people, and they compute the logic that would give you the answer. Now, why is this relevant? Well, remember how I said that an algorithm is sort of neither good nor bad, because it's just a tool, and how you use it is up to you. And so with machine learning, once again, it's just a tool. But if you give it a bunch of input that is highly selective, or is biased, or omits a whole segment of society, then when the machine learning algorithm runs, it's going to give a result that is unfortunately not going to match that proper thing. So when I went back at the beginning, I talked about how, a bank that's going to give a loan has an algorithm to determine whether they should give the loan or not. That's usually based on numbers. They crunch the numbers and they say yes or no. Well, if that's been turned into a different situation where it's entirely plausible, by the way, where someone could take your Facebook feed and look at all the pictures, and based on the pictures alone, they can have a good measure of your economic status. They can know where you live. They can see the kind of things you do. And based on that, they could generate a risk factor just by the images on your social network feed. And then with that risk factor, they can say, no, we're not going to give you a loan. Now, that to me is a challenge. Like that is sort of where the algorithm starts to change, where it's no longer trying to solve a problem. They're using it as a way of minimizing risk. you see the difference? And so instead of having a specific goal in mind where I'm trying to sort all these items, or I'm trying to find a word in a long table, they're trying to determine, well, if I have the following input, is it the right answer because of risk to give them the following answer? And so it's a much more general kind of solution. And I know that we've gone a little bit further afield, but it's worth mentioning that this word algorithm has now become two different meanings. Up until now, most computer scientists would have the algorithm idea like we had in the 1970s. But now going forward, when you see the word algorithm now in the media and the press, it's really starting to be what's called a machine learning algorithm, which is a new kind of thing. And it's the real challenge there is that it almost removes the human from the loop entirely. You can, for example, one of the most common ideas is like license plate recognition. If you give this machine learning algorithm 100,000 license plates, then it can use that to very quickly write some code. It generates the logic so that when you give me an image of a license plate, it'll just read off what it is. And that's a really powerful thing. That's a really nice algorithm to have. But you can see how this turns into a problem if you use facial recognition. And then that's the thing you use for, oh, I've recognized the face, and that's my answer. And it starts to become dehumanizing again. So as long as you're solving a problem that's very clearly defined, then I think the algorithm is just an algorithm. But when it's used in a way that has an impact on you as a human, or it changes the very society that we're in, that's when you have to be careful.
Yeah, I mean, that's fascinating, actually. And you're right, actually, to bring up machine learning. But like you also say on the flip side, there is still a human element to a sense that, it's still someone programming the initial thought process of the machine, as it was. So there's never going to be almost like 100% non-biased, because the person who's actually programming themselves are using based on their opinion, their biases. That's how they're programming the initial machine learning. Like you say, though, if you're using it with clear defined goals and purpose, then in theory, there's no problem there. It's just the human element that makes things, as always, a little bit complicated. Yeah.
Yep.
No, I agree. And this actually leads really nicely to talking about your book, Learning Algorithms. I know we've obviously touched on algorithms quite a lot in this conversation, but why don't you give the listeners an idea of what your book is and really just lay it out?
Okay, thank you so much. So I've been teaching algorithms and software engineering for 25 years, and I'm teaching to undergraduates in computer science. So these are students who have dedicated their initial years to learn this field of computer science. And the challenge is there's millions, billions of people who really just want to learn computing, and they're already a professional. So they don't have the time to go back and get an undergraduate degree in computer science. And I'm going to argue you don't need an undergraduate degree to learn about algorithms. And so what you really need to do is find a way to learn about it on your own. And so one of the challenges with that is we have so much material online that you think you can just go to a website and you can learn everything you need to know. But that's really hard if you're coming outside the discipline to try to learn what an algorithm is. So when I put this book together, what I really tried to do is always think about the person who was an electrical engineer or an accountant, and now they're just trying to learn how to program for the first time. And so I produced the book in a way that provides a very linear representation that says, start right here in chapter 1, and I'll start with the very simplest things I can. And as I need to introduce more complex things, I will do it at the right time. So it gives you the opportunity to learn algorithms, which is sort of the why we named the book that way, as opposed to me teaching you algorithms. Because if you're teaching algorithms, we all understand that you're in a classroom and there are students there and they're ready to learn. But if you're trying to learn algorithms, well, you're on your own and you're trying to figure it out by yourself. So there's a lot of visuals. There's a lot of decisions we made in how to represent things. I chose to use the language Python because it's a very easy to learn language. It's very popular, not just by computer scientists, but by non-computer scientists as well. And I think I just read recently, it became now the most popular language but initially Java has been the most popular language since like the mid-90s. And now Python became now the most popular language, which is hard to judge, of course, but it's based on statistics that people have developed. And so because Python is so popular, I thought it would be great to use that language to reduce the barriers that someone could look at this book and say, well, I really want to improve my coding. I really want to learn how to write more efficient code. And to do that, like I said, you need to learn the data structures and then the algorithms. And so with my book, I'm hoping it provides a lot of good visuals. All of the code is available, of course, because it's open source and you can retrieve those all. And then hopefully by looking through my book and looking at the code, you will be able to understand the algorithm and apply it in your own systems.
Okay, wow, thank you for explaining that. And I love that analogy as the reason why you called it learning algorithms. You know, reminds me of the parable of teaching a man to fish rather than you supplying the fish. So it's very, you know, eloquently, you know, designed in that sense. You know, we're talking about algorithms, so it fits in quite nicely. And for people who want to buy the book, where can people actually buy the book?
So I know you can always buy it on Amazon because that's a good delivery mechanism, which, by the way, Amazon has their own algorithms that they use to set the prices effectively. So again, it's a way, I just want to bring that in. So you get on Amazon, the company is O'Reilly Media, and they have a lot of online materials. And so it's probably true that your local library or your company already has a site license to access all of the material that's in there. So you can get it online that way. You can also get it via Kindle because that's the way people read books these days. So there's plenty of opportunities for you to just find this book on there. Obviously, if you're going to Google it, both learning and algorithms are such popular keyword terms that you might not find the book. But if you say learning algorithms and my name or learning algorithms and O'Reilly, you go right to the book.
Fair enough. And you know, when you wrote the book, what was your favorite part of writing the book?
So what I found most interesting, and that's again, what I like is usually interesting, right? What I found most interesting was trying to find a way to imagine someone who doesn't have the background and to make sure that I never leave them totally lost. So I have to always think as I write this paragraph, do I still have the reader with me? And of course, I don't know because they're not with me. So what the favorite part I had in writing the book was working with some early readers. The book was released chapter by chapter online. And so a lot of people started checking it out while the book was being read, was being written. And I got some good feedback that helped me orient the later chapters. So I think that the book actually got better as I started writing because I started getting more feedback on the things that worked, the things that, oh, I'm still lost here. Why is this the case? And that helped. So for me, it's more like a meta thing. It's not so much any one part of the book. It's the whole writing of the book, the way that I really try to lay it out in a linear path, which is so hard. Like what exact sequence of things do you need to know to learn? And it's like just-in-time learning. Just make sure I don't overwhelm you and keep you focused so that by the end of it, you can be almost amazed, like, wow, I was able to get through that and I never was totally lost.
Okay. And, you know, obviously this is a bit of sort of big yourself up sort of thing. So why your book? There are books out there already about algorithms and, you know, perhaps, you know, people have already purchased one or two, don't know about your book. Why should they go for your book?
Okay. Again, that's a nice, for me, easy explanation. So there's a good number of algorithms books. There are 5 top bestsellers, and they are great if you're teaching an undergraduate or a graduate class in algorithms. The main book is like 1,500 pages. And when you look through it, it has everything you could possibly want if you're a computer scientist. But if you just want to know how to make your code faster, you won't find it in the book. It's always implied. And so books that are in the press that have proofs and lemmas and what's called pseudocode, where they just sketch the idea of the algorithm, they're great as a teacher because then I give it to the student and I say, okay, now it's your job to try to figure it out. But this book, the one I was writing, was trying to reduce that friction and say, I know you're trying to learn this, so I'm not going to stand up on a stage and tell you 2 hours of introduction material. We're going to go right to the heart of the question. We're going to always have in mind that you're trying to learn something right now. And I'm going to teach it to you so you always learn something almost on every page as you're stepping forward. Instead of like most textbooks, the first chapter is always introduction. And it doesn't have anything worthwhile. It just talks about notation and what's about to come. And I really try to focus right on the idea that you're here, you're busy, you don't have time for an undergraduate course, you just want to learn this. And so I'm here to show you how you learn it. So that's the reason that my book is different than the other books.
Okay, fair enough. I'm certainly sold. And what we're going to do is put all the, the links relevant to for people to buy the book in the description as well. And so if people want to buy it and really want to support yourself as well, we'll do that for you. We also want to give you the opportunity to also, if people want to reach out, if if you have a website or if you're particularly on social media, how can people reach out to you if you want to ask you for more tips on algorithms or just any sort of business inquiries?
Okay, so I do have I have a LinkedIn presence because that's my professional network. So that is one place that you could find. One of the things that I've tried to do is put together the material of the book on GitHub. So if you go to my GitHub page, I have about 20 repositories. So there's a lot of things that are there. And so what I would suggest if that they have, for example, if they have an issue with something that came up in the book, well, go to the GitHub repository and make an issue on the repository, which is the way open source kind of works. And that's sort of my preferred strategy for that.
Okay, fair enough. And we'll put it on the screen as well for people to see the link to your GitHub and LinkedIn and all of that sort of stuff. All right, so going back to algorithms then, do you have a favorite algorithm and what is it?
Right. So what I think about is that first one. I learned how to program in a language called BASIC, which really is basic. And then the next language I learned was Pascal, which is a nice mathematical developed in the 1970s. And so what I remember most was when I first learned about this data structure called a binary tree. Now, the binary tree is a fundamental data structure in computer science. It's like the godfather of all computer science data structures. It shows it is computer scientists' best contribution to humanity, right? Mathematicians have done all kinds of things that lead to engineering, so people can build bridges and can build cars, and that's what math does for humanity. They can send people to the moon. What does computer science do? So we come up with the very fabric of computation and make it possible for computers to run effectively. That's what computer scientists do. And so what a binary search tree does is it allows you to structure data in a way that is completely different from the way humans do. So we're category people. We make lists, long lists, and you've got to keep them in sorted order so you can find things like a dictionary. And so just imagine you've got a dictionary. Now you want to add one word to it. Oh, well, I've got to put it in the middle and reprint all the pages that come after it, right? It's very labor intensive. What a binary search tree does is it fragments things up. So you just store things in memory and you just have references to them all. And there's a lot more complexity to that. But what it allows you to do is store billions of values and you can change them effortlessly because you're no longer stuck trying to keep things in a long linear list. It just makes it so efficient. And once I saw that, that to me was the eye-opening part where I no longer was thinking of storing things in an array, which is like a long list of things. But then I started thinking about storing them in this very dynamic, highly fragmented way. So whenever you need something, you just quickly go to it. As an analogy, for example, we may have heard of the 7 degrees of Kevin Bacon, like this idea that you're here and you know one person who knows one person who knows, and before you know it, you know someone who knows Kevin Bacon. And you're like, oh, I'm just 7 steps away. And it's a sense of how in a very large space, you're really not that far away from something you're looking for. And so in a binary search tree, you could have 1 million values, but you're no more than 20 steps away from any one value in that collection. And so instead of looking through all the 1,000,000 one at a time, I just look at 20 and I find the one I'm looking for. And that's because 2 to the power of 20 is about 1 million. And so this data structure, once you recognize it, it opens up the door for all the other data structures that we use to store amazing things and help you with GPS planning as you're on a mobile device trying to chart your course in a Waze application to I've got 10 million books and I want to find the one I'm looking for. And oh, by the way, I'm going to get another 500,000 tomorrow. Don't worry about it. You just store it and you can quickly find everything. So yeah, for me, it was learning about the binary trees. And so if you're a programmer and you just want to get to the first really interesting data structure, that's the first one I would tell you to go to. Learn about binary trees. And once you've done that, it's going to open up the doors to so many other possible things.
I can actually relate to that. Actually, when I was in university, that was actually the first algorithm I learned as well, actually. And it really did open my eyes to the power of, computer science and how you can really do things really efficiently. And it actually, as a human being, just naturally made me understand the way of the world a little bit more and how things naturally work. So you can, become more efficient with your schedule, for example, how you efficiently plan your time, how you, interact with people in particular as well. What's the best use of leveraging your time ultimately. And I think for me, someone who studied computer science, that, binary search, that algorithm, just understanding, the essence of it really helped, my understanding. And I know for a lot of beginners, that is, as you say, like a good entry point. On the converse, is there like maybe a complex or maybe, an algorithm that is just purely just interesting because of the complexity or the detail of it? Maybe people are, who are listening are, experts with algorithms. Is there one that you can put people onto?
Yeah, so we'll start with a question. And it's actually called the London ambulance problem. So you're in London, and so you've got all these citizens, streets, and everything. So where do you put your ambulances so that you are no more than 2 minutes away from any person? You like pick a number, and you've got the whole map layout of the streets of London. And where do you put your ambulance stations? So that's a computer science problem. And there are numerous techniques to try to figure that out. And so one of them is a really interesting one, and it's called a Voronoi diagram. It's Voronoi, and it's a technique that develops this spatial structure. It's like a network. When you look at it, it looks like a spider web. And when you look at that, what you're basically saying is that I've divided up my space, in this case London, into these regions. And so if you're in that region, you put a dot and you say, that's the ambulance that's closest to anyone in that region. And that idea, that structure lets you solve that problem. It also lets you solve a problem like, I've got a big open brown field that's got some chemical waste or other waste. Where do I find the ones that are the greatest offenders so I can start with them first? And so you lay out the grid, you find what are the parts that are closest to this very dangerous place. And then once you identify that, you aim your cleanup attention towards that. And so it's this idea that you have a general problem that you're trying to solve, and you solve it by creating this really intricate structure that allows you to answer the problem. And so for me, I came across this back when I was in college, and it's just so amazing as a computer scientist, because if you really want to implement that from scratch, it's not like climbing Mount Everest, but it's like climbing a really good mountain. Like if you can implement that, you have some skills, and that's like a challenge, right? Like, why do people run marathons? They want to challenge themselves. If you're like programming and you want a challenge, pick one of these really interesting algorithms and say to yourself, all right, I'm gonna try to do that. And that's by itself, it's a good way of measuring your skills. You learn so much when you're trying to implement them from scratch. So for me, that's the one. It's trying to find the right structure to be able to answer these really interesting real world problems in an efficient way.
Okay, that's great. And I guess, is that the official name, the London ambulance problem, or is that something you came up with?
No, there actually is. It's called the London ambulance problem, and they use it for a number of things. But the official name is the Voronoi, Voronoi diagram, which is a structure that lets you answer kind of problems like that.
Okay, awesome. And I guess, finally, as we wrap up, I normally do this thing sometimes called the Mount Rushmore of computer science. It could be tech. It could really be anything that's, really pertain to you as to where you are now in your career. So, who is your top 4, your Mount Rushmore? Starting with, it doesn't have to be a particular order, but just give us the first one and why, and then we'll go sequentially down to the 4th one.
All right. So we'll start with Don Knuth, Knuth. Don Knuth is an American computer scientist. He's still with us, which is amazing that so much has actually happened, and these towering figures of computer science are still with us. So he is a professor of computer science, and what he did is he basically founded the field of analysis of algorithms to really explain not just, oh, your code is fast, but to explain why it's fast, because the programming language can change, the computer you're running on can change, but the thing that doesn't change is the algorithm, the logic, the basic ideas. And so when he was an undergraduate, and he accepted a book offer to write a book on the art of computer programming while as an undergraduate. So he started writing and he never stopped. He hasn't finished. He's got 7 volumes. The first 4 volumes came out after 15 years. The last 4 volumes, I hope he finishes them. Like, he's been working on it for 50 years. And it's just a towering work. And they are just, if you're trapped on a desert island and you only have a set of books to bring, and if you want something that's, of course, I would bring Les Miserables, or I would bring, something like that. But if you want something technical, you'd bring the art of computer programming, and you would be able to work for years with that material. So Don Knuth is number 1. Number 2 is someone called Edgar Dijkstra. He's a computer scientist from the Netherlands. And much like Don Knuth, they were both physics majors in undergraduate, and then they moved on to computer science. Dijkstra came up with some of the most powerful algorithms that we know. He just had a knack for doing these things. And so he's the number 2. And again, it's also because of the name Dijkstra. It's spelled Dijkstra. I've typed it enough times in my life that I now know how to spell it effortlessly. The third one is a fellow named Sir Tony Hoare. So he got knighted because of his contributions. He's a Brit, and he got, back in the 1950s, he invented an algorithm called Quicksort, which at the time, and even today, is pretty much the fastest sorting algorithm that we know. And the fact that it was invented is amazing. I mean, yes, Columbus discovered America, but it was really there all along. It's not like he invented it, right? But Tony Hoare, he invented this quicksort, and it's who knows if anyone would have found it. But he found it, and it was the most effective algorithm at the time. And of course, he's gone on to do so many more things. So those are always my top 3. And much like Mount Rushmore, there's always one, Teddy Roosevelt is on Mount Rushmore, but I need a 4th. So I'm gonna go with Larry Page, who is from Google. And again, it goes back to that PageRank algorithm. And the reason why I select him is because up until that time period, most of the people who developed algorithms were doing so from like the point of view of invention, like Sir Isaac Newton. They're just trying to find things and discover new things. And since the mid 2000s, there's been a whole bunch of other people who try to take and learn algorithms and apply them as entrepreneurs and use them to found companies. And so really, this was one of the first companies that was founded on an algorithm. And so that is a blueprint for other companies who've gone on and done the same thing. So I would put Larry Page up there. And I know Sergey Brin was also involved in that, but Larry Page has always been the Facebook of Google. So the face of Google. So I would choose him. So that's my 4th one.
So thank you for sharing that. And before I wrap up, was there any final words that you wanted to say? Maybe something that we've missed in this algorithm conversation that you may want to discuss? The floor is yours.
Yeah. So what I think about algorithms, and again, programming in general, is that it's one of those skills that seems to be like a modern need. And so I have always said that anyone can learn how to program. Like that by itself is just a skill, like reading and writing and things like that. If you use Excel, you have to put formulas in there, and you can be an effective Excel person if you learn how to write some small code snippets. And this is true, that anyone can program. But then to go to the next level, if you really want to learn how to be a professional, then you have to take those programming skills. You got to find a way to lift them up. And again, I still believe that anyone can do that because it's just a kind of skill, but it takes a little bit more practice and it takes some mentoring. And that's one of the things that I would encourage anyone who wants to do this, is that there's so much information out there. All the algorithms, almost by definition, you can find a Wikipedia page that tells you what the algorithm is. And so you can learn them and you can apply them yourself within your own disciplines. So it's just an opportunity that I would say is that if you have started down the path of programming, take this opportunity now to try to go down the higher path of learning more about algorithms, because I think you will find it will lead to very effective code for you and also very intellectually rewarding.
This is a SkillStruct presentation. If you like what you hear and see, Don't forget to like, share, and subscribe.